Hello students, let us do electrical energy and the power when the current is flowing through the cross section of the conductor. Now let us consider a conductor having the two ends marked as A and B. So these are the two ends of a conductor. Let I be the current flowing through this conductor from point A to point B, or from one end of a conductor to the another end of a conductor. Let VA and VB be the potential at point A and point B, or at one end A and another point B. Clearly, the current is flowing from a high potential to low potential. That we know that a current will always flow from high potential to low potential. So there is a potential difference between the two ends due to which the current I is flowing. Let potential difference be denoted by V, and it is equal to VA minus VB. Let us name it as equation number 1. In time interval, since the current is flowing, so there will be a transfer of a charges from one end to another. In time interval delta t, let delta q be the amount of charge transported from one end to another end. That is, delta q is equal to I into delta t. Now, since there is a potential difference between the two ends of the conductor, the potential energy linked with the charge, or the potential energy of the charge, will also change. And since the current is flowing from A to B, or the charge is transported from A to B, the change in the potential energy, so change in potential energy delta U is equal to final minus initial. Now this can be written as delta Q VB minus VA, that is equal to, now delta Q is I delta T, and VA minus VB. Now we know that current flowing through, the current is flowing from high potential to low potential. So this difference is greater than 0. This difference is greater than 0. So this difference should be less than 0. So I will write this as minus I delta T into V. V is VA minus VB. Here we have VB minus VA. So the change in the potential energy is minus I delta TV, where VB minus VA is less than 0. Now this is the change in the potential energy when the charge or a current is flowing from one end of conductor to the another end. Now we know that charge can neither be created nor destroyed, and the total energy of the system should always be conserved. So according to law of conservation of the energy, delta KE is equal to minus delta U. Now this relation is less than 0. This relation is less than 0. It is negative. So according to the law of conservation of energy, delta KE is equal to minus delta U. That is, energy is always conserved, and therefore delta KE is equal to I delta T V. So I write this equation as VI delta T, which is greater than 0. It means whenever the charge flow through a conductor, its kinetic energy increases. So whenever the charge will flow from one end to another, its kinetic energy should increase according to this expression. Now if the kinetic energy increases, where that energy is used up, that you have to see. Now when the kinetic energy of the charge increases, let us consider what happened inside that we have studied. Suppose the electrons are moving from point B to point A, or one end of the conductor to the another end of the conductor. Now it is given that, or we have arrived at the conclusion that the kinetic energy should increase. Now as the kinetic energy increases, the electrons energy is increasing, its drift velocity should increase. So though it is not an accelerated motion, because when their kinetic energy increases, they collide with the ions oscillating about its mean position. So that we know that if their kinetic energy of this electron increases, they should gain a speed, or the drift velocity should increase. But you have to remember that inside the conductor it is not an accelerated motion, because as soon as the electrons are accelerated from one end to another, they collide with the ions oscillating about its mean position, and that kinetic energy is converted into the potential energy, and the amplitude of the ions increases, due to which the conductor gets heat up. So this increase in kinetic energy should be dissipated in the form of a heat, because the amplitude of the oscillation of the ion increases and they collide with the wall of a conductor. So this expression says that whenever there is a motion of the charge, the kinetic energy of the charges do increase, but that increase in the kinetic energy is dissipated in the form of heat energy, and we will derive how much heat energy is dissipated, or how much power is dissipated, or there is a loss of a power due to the collision of electrons colliding with the ions which are oscillating about its mean position. So let us see how the dissipation of energy take place. So we arrived at the conclusion that the kinetic energy of the charge should increase, but they collide with the ion, due to which the conductor gets heat up. Now there is a loss of energy, clearly there should be a loss of energy. Now how they obtained this kinetic energy, how their kinetic energy increased, and how that kinetic energy is converted into the loss or a heat loss. So let us consider a simple electrochemical cell. Now we have to find out that when the charge flow from one end of a conductor to the another end of a conductor, this expression says that its kinetic energy should increase. But from where they get this kinetic energy? Also we know that current will not flow by itself. You have created the potential difference, so the current is flowing from one end to another. So what is the source of this creating a potential difference? So that the source is the electrochemical cell. So let us consider an electrochemical cell, a simple electrochemical cell which consists of an electrolyte. So we will see the structure also, what happened inside the electrolyte. So we have seen that what happened inside the conductor. Now in the coming lecture we will also see what will happen inside the electrochemical cell also. So this simple electrochemical cell consists of electrolyte and two electrode, where one electrode is positive and another electrode is negative. So electrochemical cell will convert the chemical energy into say light energy, or if we have connected a conductor, it should convert it into a heat energy. So if I use this chemical cell and connect it with a bulb, I know that the chemical energy will be converted into the light energy, but there is always a loss of energy. So today we will connect a conductor, and we know that every conductor has some resistance. So in fact I will say that connect these two electrodes with a resistance R. So one is plus terminal, one is negative terminal. So what we have talked about a conductor. Now let R be the resistance of this conductor, because no conductor is an ideal conductor. It means every conductor has some resistivity or resistance. So let R be the resistance of a conductor. Now this conductor is written as R. Now we have connected this because this conductor has a potential difference. So this potential difference is due to the electrochemical cell. Now what will happen? This is our end A, this is our end B. Now the current will flow from A to B. Again, we assume that now the potential difference of this two electrode is V, that is VA minus VB, which was positive. And this potential difference created the potential energy difference, due to which the kinetic energy of the charge inside the conductor increase and they collide with the ions, due to which this conductor gets heat up. Now if it gets heat up, there is an energy loss, or we get a heat energy. So if I have connected only a conductor or a resistor, the chemical energy will be converted into heat energy. Now how much heat energy is produced, or you say dissipated, in the form of a loss? So if you connect a bulb, that bulb will also have some resistance. So we will find out how much loss of the energy take place in that bulb. Though that bulb will give you the light energy, but this entire chemical energy will not be converted into the light energy. It should be the chemical energy will be converted into the light energy plus heat loss. So today we are concentrating on a power loss or a energy loss. Now the current is flowing from one end to the another. This is increase in the kinetic energy of the charge, and this increase in the kinetic energy is converted into the potential energy of a ions. Now we continue this. From where they get this kinetic energy? We say that the kinetic energy increase, but from where they got this kinetic energy? So clearly they got their kinetic energy from this electrochemical cell, from this electrochemical cell. So whatever energy, that is a chemical energy, this cell have, it will be converted into the kinetic energy of the charge, and that kinetic energy of a charge will be dissipated in the form of heat energy, because inside the conductor the potential energy of the ion increase, or their amplitude increase, and they collide with the wall of a conductor. So according to work energy theorem, now this is the increase in kinetic energy. Now let delta W be equal to delta Ke. That is the work energy theorem. In fact, I can write delta W, instead of that, work done is equal to change in the kinetic energy. So therefore delta W is equal to Vi delta T. This work done is equal to the heat energy, that is Vi delta T. So this much heat energy is produced across the conductor or a resistor having a potential difference V. So if V is the potential difference of electrochemical cell, we assume the resistance of the wire is negligible, and later on we will see that a cell also have an internal resistance. So we are assuming there is the internal resistance is not very large, and the wire also does not have any resistance. So we have the entire chemical energy should be converted into the heat energy. So that heat energy is equal to the potential energy, the potential difference, V is potential difference across the conductor and the current I flowing through it, multiply by the interval for which the current flow through this resistor. So this is referred as the loss, heat loss. Now, heat energy per unit time is VI, and therefore the power is equal to V into I. So this is assuming there is no loss inside the cell, there is no loss in the wire. So I can say this much power is produced by the cell and same amount of power is dissipated across or in a conductor. So if there are no losses anywhere, neither inside the chemical cell or a conducting wire, I can say this much power is produced by the electrochemical cell, and the only device which is connected to the electrochemical cell is our conductor. So this much power loss should be there across a conductor. So this is one expression for a power. Now Ohm's law is applicable to a conductor, so V is equal to IR. So P is equal to I square R. This is the power loss across a conductor. So this expression can be used to find out the power produced by the cell and the power loss across the conductor is the current flowing through it and the resistance of that conductor. This is one conductor. If there is another conductor connected to it, say R1 and R2, then the power loss in that will be equal to I square R2 because current will flow in the resistor. So generally this expression is used to find out the power loss. So this is the second expression. Now here the relation was between V and I, here the relation is between I and V. Also power is equal to, now if I eliminate this I can be written as V upon R. So P is equal to V square upon R. So these are the three expressions for the power dissipated across a resistor having the potential difference V. So this expression should be used. You have to remember this V is the potential difference across the resistor or across a conductor you have connected in the circuit. Otherwise, it is better, see that if I have another resistance, say this is R1 and R2, then if this is a say 5 volt cell, then you cannot say the power loss in this is phi into current or phi into current this, because the potential difference, we know in a series combination the potential difference is different. So if I have to find out power loss using this formula, first I have to find out potential difference across R1, potential difference across R2. Then the current is same. Then I can write P1 is equal to V1I, P2 is equal to V2I. And VI will be the power produced by the battery. So you have to remember while applying this V formula. It is easier if I apply the power loss formula to be I square R, because I is same in this expression. So it can be written as I square within bracket R1 plus R2. So these are the expression for the power losses or the electrical energy. So this much electrical energy, whatever kinetic energy is gained by the charge. So actually what happened, this much is a kinetic energy gained by the charge inside the resistor or inside a conductor. Now that gain in the kinetic energy in ideal situation is equal to the loss in the resistor. So we say that inside the conductor the motion of charge is not an accelerated motion. All the electron move with the average drift velocity. They move with the average drift velocity because as soon as they get accelerate, they collide with the ion, thereby transferring their kinetic energy into the potential energy, and again that potential energy of the ion is converted into the heat energy. So if there is a heat loss, I can use I square RT because power loss is equal to heat energy or energy lost per unit time. So this is all about the electrical energy and the power. Now let us see, if this wire have a resistance, then how much power is lost in this wire also. Now see, in the coming lectures we will study a device which is called transformer. Now in order to transfer the power from the power station to our house or to an area, the voltage is kept as high as possible and the current flowing through that cable should be low. Now why it happens, or what is the logic behind it? So wherever you see a cable which is transferring power from power station to the area, there is a sign of danger because the voltage or the potential difference across it is very high. So while transferring your power, you have to increase or decrease the voltage, and that is the use of a device which is called as transformer, which we will see in the coming chapters. We will see that transformer is a device which will be used to increase the voltage or decrease the voltage. So that device will be a transformer, which are of two types, setup transformer and step down transformer. So we will see how the power is transmitted from one end to the another end or over a large distance. So while transferring a power over a large distance, you have to see that the voltage is very high. Now let us see how the voltage is very high, or why the voltage is kept very high. Now let us see how the power is transmitted, the basic knowledge. We will come to this topic in details while studying the transformer. Now let us assume that this is a power station. This is a power station which is producing an electricity or a power. Now this is the cable wire, and this is an area or a city where the power has to be transmitted with the help of this cable wires. Now since the length of this cable wire is very large because it is connecting a power station to an area or city, the resistance of cables is very high. Why the resistance is very high? Because R is proportional to L. We know that R is equal to rho L by A. So that the power resistance of this cable is very high. Now it is clear that if the resistance of the wire is very high, the power loss is also very large in this cable wire. These are the power losses. So if resistance is very high, there will be a power loss in it. These all losses are sometimes referred as the ohmic loss or energy loss, or you can say they are the power loss depending upon the formula. Sometime we call simply ohmic losses, or if it is in the form of energy, that is H, then it is energy loss, otherwise it is power loss. So power loss is very high if the resistance of the wire is very high. Now power is transmitted at very high voltage. Now why the power is transmitted at a very high voltage? Now let us assume that a power production of this station is P is equal to VI, where V is a voltage and I is the current which will flow through a cable. Let us assume the power station or a transformer also have some resistance R. So this is the power production which has to be transmitted to an area or city. Now this is connected through a cable wire. Let RC, C for cable, be the resistance of a cable wire. So according to our formula, the power loss is equal to I square RC. This is our formula for the power loss in the cable wire. Now this is the power production. This is the power production at the station, assuming the power station using the devices also have a resistance R. See, power station will also use some device for producing the energy or a power. So let the resistance of the device used in power station is R. So the power production after considering the loss there itself will be VI. So this is the power production after considering the loss across R. Now the current produced is I, or which is to be transferred from one end to another. Generally, the current is not very high, the power is kept very high. So if P power loss is I square RC, then from this equation I can write I is equal to P upon V, and therefore power loss is equal to P square RC upon V square. Now see this, the power loss is inversely proportional to the square of the voltage. Power loss is inversely proportional to the square of voltage. So if I keep the voltage very high, that is a V square, then the power loss will be minimum. So whenever we transfer a power or energy from one place to another with the help of the cables, then let us assume RC is the resistance of the cable, then your V should be very high, the voltage should be very high. Now as the voltage is very high, the power which has to be transmitted from one place to another should remain constant. That we will see in the transformer. So here P is equal to VI. Let us see the basic. Suppose the power which has the voltage or the potential difference is, now I am giving simple small values. Suppose it is 5 volt and the current flowing is 1 ampere. So the total power which has to be transmitted is 5 watt. Power has to be transmitted. So this city or area have a requirement of 5 watt. Now the power at one end, that is power at station, should be equal to the power of a city, that is the requirement of a city. A city require 5 watt of power. A city require 5 watt of power. So the power station generated 5 into 1, that is 5 volt into 1 ampere. Now if I keep this current as a 1 ampere and let us assume that the resistance is 1 ohm. The resistance of, though all these values are very high. Now I am trying to make you understand why the power is kept very high while transmitting it from one station to another. Now suppose I don't use any transformer and directly I pass 1 ampere current through this cable wire. So what will be the power loss in the cable? It will be 1 square into 1 ohm, that is power loss. So the power loss is 1 watt. So what will the city get? The city will only get a 4 watt of the power, that is a loss. This 1 watt is lost here. But I need that a city gets 5 watt of power without any loss. I need that condition. So we are deriving all this. Remember, again I am referring, if you are considering only a conductor to be connected across an electrochemical cell, then we have this 3 losses, VI, I square R and V square R, where V is clearly, it is the potential difference across the conductor. Not this V is not a potential difference of a cell. Instead of that, I use this for a power loss. Now the power generated at the power station is VI, that is 5 watt, and the CT requirement is 5 watt. Now if I directly transfer this, or I can see here the power is say 5 square generated, that is 25 into 1, 25 into 1 divided by 25, so that is 1 watt. See the power loss that I have found. So I can use this formula also. What is power generated at a station? 5 watt. What is the resistance of cable assumed? 1 ohm. What is the voltage at power station? 5 volt. So 25 into 1 divided by 25, that is power loss is 1 watt. So I can use this formula, or I can use this formula, assuming the current produced in the power station is 1 ampere, or it has been planned to transfer 1 ampere current through a cable wire. So how much power the CT will get? The CT will get only 4 watt of power. That is the loss. The cable wire will use 1 watt of power. That is 1 joule per second. Now in order to minimize this loss, the loss occurred in I. The loss occurred in I. I cannot change the RC. I need a cable. So let us assume that the power which is transmitted at a power station, the current is reduced and the answer still comes out to be 5 watts. So what I will do? I will keep a voltage 50 and the current to be 0.1 ampere. So it comes out to be 5 watt again. Now this power generation is 5 volt. Power generation is 5 volt. And before transferring, it is converted into a 50 volt. Now who will do this? So there we need a transformer. So transformer at the power station will increase the voltage. And if the power is voltage is increased, the current should decrease, because we have to transfer a constant power from one place to the another place. Now what happened? The power station has produced 50 volt. So they produce 5 volt, or the potential difference was 5 volt. With the help of transformer, the voltage is increased. This is the use of a transformer, and you will see it is called step-up transformer. So 50 volt. So again the power to be transmitted is 5. Now let us see the power loss. So power loss is equal to I square. Now the current is 0.1. So 0.1 square into 1, that is 1. So it becomes 1 by 10 upon 1 by 10 into 1, that is 1 upon 100. So say the power loss is 0.01 watt. The power loss is 0.01 watt, which was earlier 1 watt. So as I increase this, suppose I make the voltage with the help of transformer to be 500, then the current becomes 0.01. Again I get a 5, but now the power loss 0.01 whole square. So that will be more less value. So you see clearly how the power loss has been minimized. So we minimize the power loss by increasing the voltage. By increasing the voltage, you minimize the power loss. So in order to, or either if you don't get a clear idea about what I am saying, clearly you see that power loss is inversely proportional to the voltage. So earlier, when potential difference was 5 volt and the current was 1 ampere, the power loss was 1 watt. But as I make a potential difference 50 and say a current 0.1, again I get 5 watt, the power loss reduced to 0.01 only watt. So I keep on increasing the voltage as large as possible. So I can make 500, then 0.01, 5000, 0.001. Now when we come to this part, here the potential difference arrived is 50 volt and the current is only 0.1 ampere. Now this large potential difference will damage our instrument, or this current is not sufficient for the device to work properly in our house. So what will happen? Again, this 50 volt will be converted into 5 volt again with the help of transformer, and such transformer will be referred as step down transformer, and as this potential difference will decrease, the current will restore to 1 ampere. So this is how the transformer, or this is the principle which we will study in the transformer, that why we need a step up or step down the voltage. So at power station generally we have a step up transformer. In our area you will see in your area or in your surrounding there are large transformers. So that transformers are step down because the potential difference from the cable wire, or the potential difference across the cable wire is very high, and the current flowing through that cable wire is very low. So you try to understand this concept. I tried to explain the basic concept of a transformer. Otherwise, we can see that power loss is inversely proportional to the potential difference. So this is what we have for today's lecture. Have a nice day.